The topic is exponential and logarithmic series. Firstly, let's revise from exponential function. Let's define exponential function first. That is a function in which a constant quantity is raised to a variable power is called an exponential function. For example, y equal to a to the power x or y equal to 2 to the power x etc., where a and 2 are the constant and x is the variable. And next part is the number. E is called Euler's number. Which is a special base of an exponential function, e to the power x. The number e is defined as that e equal limit n tends to infinity 1 plus 1 by n to the power n, or e equal limit n tends to 0 1 plus n to the power 1 by n, and the value of e lies between 2 and 3, that is approximately 2.718. This is the introduction of exponential function. Now let's move the logarithmic function. Second part is about logarithmic function. About logarithmic function, if a greater than 0, be any number, and x and y be any other two numbers, such that y equal to a to the power x, then x is called the logarithm of y to the base a, and we write x equal to log a y, Then let's move to the theorem, dear students. that is theorem number 1, that is expansion of e to the power x. So the statement is, for all values of x, e to the power x equal 1 plus x by 1 factorial plus x square by 2 factorial plus x3 by 3 factorial plus infinity. Yes, we have to prove this. Yeah. Now, dear students, we have to discuss about the proof. We know by the binomial theorem. We know by the binomial theorem we know 1 plus 1 by n to the power nx equal, in this format we can discuss 1 plus nx times 1 by n plus nx minus 1 by 2 factorial 1 by n whole square plus nx minus 1 nx minus 2 by 3 factorial 1 by n to the power 3 plus then n cancel, 1 plus x by, this can be 1 factorial plus, we can write 1 factorial as 1, and here will be n square, we can cut this n and this n x, if we have taken n common, x minus 1 by n, we can express in this way by 2 factorial times 1 by n square, and plus here n x, here n common, x minus 1 by n, here also n common, x minus 1 by 2 by n, all by 3 factorials times 1 by n cube, and plus. So it can be written as 1 plus x by 1 factorial, this n square n cut, plus x minus 1 by n by 2 factorial plus x by 1 by n, x minus 2 by n all by 3 factorial plus then we have to move to the next step. We also know e equal limit n tends to infinity 1 plus 1 by n to the power n. Therefore e to the power x equal limit n tends to infinity 1 plus 1 by n to the power n whole power x. So it can be written as limit n tends to infinity 1 plus 1 by n to the power nx. So here you can see this part and this part is same. So substitute that value. Therefore e to the power x equal limit n tends to infinity and this one n tends to infinity 1 plus x by 1 factorial plus x minus 1 by n by 2 factorial plus x minus 1 by n x minus 2 by n by 3 factorial plus equal, then we can apply the limit n tends to infinity. Then what we obtain here, we obtain 1 plus, here we obtain x by 1 factorial plus, here 1 by infinity is 0, x square by 2 factorial plus, here also 0 0, x cube by 3 factorial and so on. Proved. In this way we can prove the value of e to the power x. Now some useful results. We know, just we proved e to the power x equal 1 plus x over 1 factorial plus x square by 2 factorial plus x cube by 3 factorial and so on. This is supposed by A. First, replacing x by minus x, then what will we get? E to the power minus x equal 1 itself 1 minus x by 1 factorial plus x square by 2 factorial minus x whole square will be plus minus x cube by 3 factorial and so on. This is condition number B. And replacing x by 1 and minus 1 respectively in A. First changing x by 1 and x by minus 1. Then what will be e to the power 1 equal 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial plus so on. This is number C. Then e to the power minus 1 equal 1 minus 1 by 1 factorial plus 1 by 2 factorial plus minus 1 by 3 factorial and so on. This is the condition number D. So after that derivation, next you can try 1 by 2 e to the power x plus e to the power minus x equal e to the power x and e to the power minus x. You will obtain 1 plus, check from above, 2 factorial plus x to the power 4 factorial plus x to the power 6 factorial plus so on. Similarly 1 by 2 e to the power x minus e to the power minus x equal x by 1 factorial. Here order you can find x cube by 3 factorial plus x to the power 5 by 5 factorial and so on. These are some results. And similarly 1 by 2 e plus e to the power minus 1 equal 1 plus 1 by 2 factorial plus 1 by 4 factorial plus 1 by 6 factorial. And one more result 1 by 2 e to the e minus e to the power minus 1 equal here 1 factorial 1 by 1 factorial plus 1 by 3 factorial plus 1 by 5 factorial and so on. It can be used in the derivation part in the examination, not exercise. Next theorem number 2. Prove that E lies between 2 and 3. So this is given. Now proof. We know that we have already derived E equal 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial plus so on. equal to plus 1 by 2 factorial, that e to the power x, you know that we keep the value of x equal to 1, then we obtain this plus 1 by 3 factorial plus dot 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 dot. Hence e is greater than 2, because 2 plus something is 2, so that is 2 is, sorry, e is greater than 2, the condition number 1. From this we find that. And again let's check many consequences. 3 is greater than 2, 3.2 is greater than 2.2, 3.2.1 is 3 factorial is greater than 2 to the power 2. So reciprocal 1 by 3 factorial is smaller than 1 by 2 square. Again 4 is greater than 2, 3 is greater than 2, 4.3 is greater than 2.2, 4.3.2 greater than 2.2.2. This is 4 factorial greater than 2 to the power q, and the reciprocal 1 by 4 factorial is less than 1 by 2 to the power q. Also 5 is greater than 2, 4 is greater than 2, 3 is greater than 2, then 5.4.3 is greater than 2.2.2, 5.4.3.2 is greater than 2.2.2.2, 5 factor is greater than 2 to the power 4, 1 by 5 factorial is smaller than 2 to the power 1 upon 2 to the power 4. And from these examples what we obtained, what we generalize, similarly 1 by 6 factorial is smaller than 1 by 2 to the power 5, and so on. And the result is, what's the result? In general it can be written as 1 by r factorial is smaller than 1 by 2 to the power r minus 1. This is our learning from this case. 1 by r factorial, that is 1 by 6 factorial. Suppose r is 6, then it should be less than 2 to the power 5. It can be written as in this way. We can generalize, or you can learn this, we can note it. And now dear student, this case, 4 case we can add 1 by 3 factorial plus 1 by 4 factorial plus 1 by 5 factorial plus 1 by 6 factorial plus less than 1 by 2 square plus 1 by 2 cube plus 1 by 2 to the power 4 plus 1 by 2 to the power 5. Again we have to convert in the pattern, adding 1 plus 1 by 1 factorial plus 1 by 2 factorial on both sides, then we get, adding this in both sides, then what will you get? Let's see. Left hand side become 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial plus 1 by 4 factorial plus 1 by 5 factorial plus 1 by 6 factorial smaller than 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 2 square plus 1 by 2 cube plus 1 by 2 4 plus 1 by 2 to the power 5. Then this is whole, this is e less than, this is 1 plus, others can be written as 1 plus, this is 1 and this is 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus 1 by 2 to the power 4 plus 1 by 2 to the power 5 plus dot 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 dot. So it is E smaller than 1 plus 1 by 1 minus 1 by 2 is, you know, the sum of infinite series that is in GP is this: A equal to S infinitive equal to A by 1 minus R. Using that pattern from this, E is smaller than 1 plus 2 1 the 2 minus 1 1 by 2, 2 goes up, 1 plus 2, E is smaller than 3. This is second condition. Therefore from first and second condition we get E lies between 2 and 3. In this way we can prove this theorem.